All right, y'all, here we go. We are on chapter 16, and this is our last chapter that we'll be covering in 101. And we're going to be looking at nuclear chemistry. So in this first one, we're kind of give a little bit of an overview a little bit, and then we'll get into some information about radioactive decay and some of the applications. So let's first get started by thinking, what do you think about when you hear the word nuclear chemistry? All right, so when you think nuclear chemistry, okay, you might have some images that come to mind or some words and thoughts, such as you might be thinking, oh, hey, nuclear chemistry, this is something that's scary or it's dangerous. You might be thinking about the atomic bombs that were dropped in 1945 or the Chernobyl disaster in 1986. Let's see, let's get a couple more pictures out here. You may also know about some of the uses of nuclear chemistry. There's use in medical diagnostic tests or even in the treatment of diseases such as cancer. All right, so radiation, here's a couple more pictures. You might think of a nuclear power plant. I think I have one more picture there. Of course, that's the one you really are thinking about, right? The Hulk. I think I'm not a big superhero person. I should have done some more research, but I think he was hit with gamma rays, and instead of dying from these, he turned into the Hulk. I do have to say that I have been at Universal Studios recently, and the Hulk is now my favorite all-time roller coaster. Might change depending on more roller coasters I go through, but it is an excellent roller coaster. All right, so nuclear chemistry. It is very important. It has so many applications in our everyday life, and our goal in this chapter is to have a better understanding of what nuclear chemistry is and how it's used around us and how we would like it to be used even more. All right, so let's just think about how initially this kind of came about, and we want to talk about alchemists. All right, so this was like a precursor to modern science, and these were people that wanted to make gold. Basically wanted to take some everyday metal, okay, like lead, and try to get this to be something that was actually worthwhile and valuable, like gold, okay? So they were trying to transform one element to another, and these were not very successful at all. So alchemists, not successful, and it was not possible to take an ordinary chemical reaction. This is all the reactions we've been studying up till this point in time have been chemical reactions. It is not possible to take those and actually transform the nucleus to go from one element to another. So far, all of our valence equations, you've seen the same number of atoms on both sides, reactant and product, okay? You might have a chemical reaction take place where you're making something new and bonds are broken, new bonds are formed, but when we balance these, the number of atoms on both sides were equal. There was the same number of sodium atoms on both sides, or carbon, or hydrogen, whatever it is. So we have not been changing the nucleus, going from one type of atom to another. All right, why not? And part of that is because that requires a ton of energy, a lot more than what is required for a chemical reaction. Let's look at this slide right here, and this kind of will help you kind of understand what's going on a little bit more. Nuclear chemistry is the study of the nuclei, okay? That's where the protons and the protons and neutrons are, and how they undergo different transformations. So I just want to kind of get a clear picture comparing chemical and nuclear reactions. So in the chemical, like we just said, the atoms retain their identity, and then in nuclear, they change from one element to another. So we are usually just talking about the electrons, and we're especially concerned with those valence or outermost electrons in a chemical reaction. But here we're not really dealing with the electrons. We're talking more about what's in the nucleus, the protons and neutrons. So that's the nuclear. You can change the temperature and affect chemical reactions. Reaction rates are not affected by temperature in nuclear reactions. The key thing is probably this energy, okay? So the energy absorbed or given off in a chemical reaction is very small compared to the enormous energy changes that you'd have in a nuclear reaction. Since the number of atoms are conserved, the mass is conserved in a chemical reaction, but there is a change in mass, and we're going to be using Einstein's equation relating energy and mass in this chapter. So E equals mc squared, and we're going to be looking at the huge amount of energy that's given off in nuclear reactions. All right, next slide. We have to at least mention a couple important people, right? So scientists have known since 1896 that many nuclei, okay, the nucleus, what's in the nucleus, the protons and the neutrons, are radioactive, that they undergo a type of spontaneous decay, and then they'll emit some form of radiation. Now, some nuclei are stable, and some are unstable, and the ones that are unstable would undergo radioactive decay. All right, so some of the people we need to maybe mention here. We probably should make sure you understand Becquerel and Marie and Pierre Curie. You probably have heard of those for sure. They gave us some of that initial work with understanding that material can be radioactive and some of the stuff we've learned. And I do have to say, a lot of our atomic structure, which we have talked about previously, figuring out where the protons are, where the neutrons are, where the electrons are, their mass and their size and everything else, a lot of that is tied into how we discovered that is tied into the discovery of radioactivity, and radioactivity helped us understand the atomic structure better. If you remember Rutherford, his experiment with the gold foil, he was shooting alpha particles, so a type of radioactive particle at the gold foil. So that kind of ties in there. So radioactivity, let's just kind of hit some definitions here on this slide first. This is the spontaneous emission or given off energy of particles or electromagnetic radiation. And it is important to note that every element on the periodic table has at least one isotope that's radioactive. We'll talk about isotopes and make sure that's kind of fresh in your mind in a couple seconds here as well. And then a couple other things to know. All elements that have an atomic number, do you guys remember what atomic number is? We'll talk about this in a second too, but this is the number of protons, okay, is your atomic number. So any element with an atomic number or number of protons greater than 83 are unstable and therefore then radioactive. They will undergo some type of decay. And then atomic number greater than 93, these ones only exist on Earth when they're created. Okay, and we'll talk about some of those processes involved which would create a new element. All right, and so radiation then, so radioactivity is this emission of particles, and then radiation is the emission of energy as waves or some type of particle. And we'll talk about radiation more at the end as well. All right, so let's move on next to one. Well, this is our review. We need a little bit of a review just to remember things. So we'll be talking about an element and its symbol or a nuclide symbol. We'll also be talking about mass number and atomic number. All right, remember this is way back from an early chapter. The mass number is your number of protons plus the number of neutrons. So if you add those up, you get the mass number, and the atomic number, like we just said, is the number of protons. That P plus, let me just make sure we all get this. P plus is protons, and neutrons have no charge. So I have a little lowercase n and a 0 there for no charge. This would be the symbol, okay? So this would be the element symbol from the periodic table. We give atomic number, has the symbol Z, so that's the number of protons, and you put that subscript low on the left-hand side, and then superscript up high on the left-hand side is then the mass number. Sometimes these are written with the atomic number left off, so you might get like this instead. And you would just need to know, if you knew the symbol, you could then go look on a periodic table and figure out what the atomic number is, the number of protons you find from the periodic table. Now, different elements can have different mass numbers, okay, but if they're all talking about the same element, atoms of that element will all have the same atomic number. When they have the same atomic number but different mass number, these are called isotopes. All right, and these would have different masses. Remember that the mass of an atom comes mostly from the protons and the neutrons. Neutrons are a little heavier, but pretty much protons and neutrons are fairly equal in mass. Electrons are very small in their mass, okay, so sometimes they're often ignored. Protons and neutrons are in the nucleus, okay, which is very, very dense and very, very small compared to the size of the atom overall. And then the electrons are in the mostly empty space outside of the nucleus. One other term to throw in, a new one, but it kind of makes sense. The particles that are in the nucleus are called the nucleons. So these are the particles in the nucleus, which are the protons and the neutrons. So the total number of nucleons would be the number of protons plus the number of neutrons. Another little note to talk about nuclide is each unique atom. So you can just talk about a specific isotope or a specific nuclide. We'll talk about that in a second. So let's see, the next one is right here. We're going to make sure you kind of get this all checked out. So I want you to look at this little example just to make sure that we got these terms sticking for you. A nuclide with 47 protons and 62 neutrons has what nuclide symbol? So I want you to write the symbol with the mass number and the atomic number, and then add up the total number of nucleons for this. So take a little pause, get your answer, and then we'll continue on. All right, hopefully you got your answer as well. But when we're looking at this, I am asked for the symbol, and I'm told we have 47 protons. I need to get a periodic table out, and I need to check when I have 47 protons, what element is that? And that is silver. All right, and so I'm told it has 47 protons, so I'm going to put the atomic number down there. And now I have to add up the mass number. It's not 47, it's not 62, it's the addition of that. The mass number is protons. Mass number is protons plus neutrons. So in this case we have 47 plus 62, and I get 109. That number goes right there. So this would be the nuclide symbol for an element with 47 protons and 62 neutrons. Now, how many total nucleons does this have? Okay, nucleons are the particles in the nucleus, which are the protons and the neutrons, which we just calculated. The protons plus neutrons, 109 nucleons total. All right, now that we've got a little bit of review behind us, we're going to be able to go on and continue into this chapter a little bit more details in the next video.